Hello everyone, welcome to lecture 39 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on super resolution with metalenses. Here is the lecture outline. We will discuss about the super resolution of metalenses, talk about the resolution limit in the conventional lenses. We will also discuss about perfect lens with sub-wavelength resolution, and then how a negative index material or NIM's lens basically works, and we will also see the limitations of such lenses. And then finally we will go to the discussion of near field super lens. We will see how we can make tunable super lens using random composites and what will be the principle of tunable near field super lens operation. So first discussion will be on the resolution limit of conventional lenses, and I believe you have studied this in optics or physics, that based on any positive index curved surface such as this convex lens, the resolution is basically limited by the Abbe diffraction limit. Now what is that limit? It says that the resolution limit or delta is typically around lambda naught divided by 2n sin alpha, where n is basically the refractive index of the medium and alpha is the semi aperture angle of lens. Now it tells you that a normal lens cannot resolve objects smaller than half of the illuminating wavelength, that is lambda by 2. Okay? So that is the typical limit. Now why it happens? If you look into a conventional lens, this is how it basically collects the propagating waves. Okay, the solid lines indicate the propagating waves, and that is how the image is formed, right. Now if you see that any object basically have got basically two kind of waves coming out of it. One is the propagating wave, the other one is the evanescent wave. Now these evanescent waves basically contain the sub wavelength details, and typically they decay and they cannot be restored, and that is why you basically only see the image that is formed by the wavelength scale resolution, okay, that is from the propagating waves. Now this is where your negative index material or NIMs will play a big role. Now if you introduce a planar slab of refractive index of say n equals -1 and you place it in the vacuum, that will basically allow you imaging with sub wavelength precision. Now this capability goes beyond the diffraction limit of the conventional lenses, and we will see this in this particular slide. So to understand how it works, we just go for the wave decomposition that tells us about the Fourier components present in the wave. So we can consider any object that scatters light and that has got components of the wave vectors in all three directions. So you can mark them as kx, ky and kz. Now the wave vector that is in the propagation direction, you can consider z as the propagation direction. So kz will be square root of k naught square minus kx square minus ky square. K naught is basically the free space wave vector. Now you can denote kt as square root of kx square plus ky square, and that is basically the transverse wave vector. Now what is the condition for propagation? So if you have kt which is less than k naught square, then this term is going to be a real quantity. So kz is real, that means the wave is propagating normally. So here you can see that the propagating waves basically can travel and carry the information about the object's large features. So there is no issue. But if you look into the evanescent condition, that is where the kt is basically greater than k naught. That means the transverse wave vector is basically the it's larger than the free space wave vector k naught, and in that case your kz becomes imaginary, and that is where wave cannot propagate, rather it decays exponentially, and this is where the information of the sub wavelength feature get lost. Okay. So evanescent waves, they are basically confined to the near field, or you can say very close to the object, and they carry sub wavelength information, that means very fine details of the object, and typically they are lost in standard imaging, since conventional lenses are unable to capture or restore these waves. and this is where exactly this negative index material will perfectly fit in, and you can make perfect lenses based on them, where you can place this to restore the evanescent waves, because evanescent waves basically grow in this kind of negative index material instead of getting decayed. So you can see that you can actually restore it to the same level where it was earlier, and then it basically enables true sub-wavelength imaging. Okay. So, in conventional lenses, just remember that they lose these fine details due to the diffraction, and that is mainly because of the evanescent waves are not being allowed to propagate or restored. So, to resolve the fine details or to have very good resolution, we understood that the transverse wavelength, that is lambda t, should be equal to 2 pi by kt. That must be smaller than the object feature size. Okay. Now, since for propagating waves, we have seen that the maximum of the transverse wave vector kt will be equal to k naught. That means the highest possible resolution is basically lambda naught. Now, conventional lenses cannot restore the evanescent waves that carry the sub-wavelength information. Thus, they are basically bound by this diffraction limit or resolution limit, right. So, you can say these conventional imaging systems cannot achieve sub-wavelength resolution. Now, we can overcome the diffraction limit using negative index material lenses, and this is where near field macroscopy approach is used. So, sub-wavelength details, as I mentioned, they are carried by evanescent waves and they decay very quickly. And if you look into the near field of scanning optical microscopy, that is NSOM, it basically collects the evanescent waves using a probe that is placed extremely close to the sample surface. And before Pendry's idea of introducing that slab of material containing negative refractive index, this was the only practical way. This NSOM was the only useful and practical way to capture this evanescent modes. However, in 2000, when Sir John Pendry proposed this groundbreaking idea that if you put a negative index material slab, that is a NIM slab, that can actually produce perfect images by amplifying these evanescent waves. So, that became very popular, right. So, this is how we understand that you can use perfect lens with sub-wavelength resolution. So, what are these perfect lens made of? They are made from negative index materials, right. So, a perfect lens is a striking application of the negative index materials. Okay. So, a planar slab of NIM can function as a lens. Often it is also called Veselago lens, okay, because he was the first one to theoretically propose the idea of this negative refractive index. Okay. So, what is striking or exciting here is that unlike a conventional lens, this kind of lens, Veselago lens or perfect lens, it has no axis or curvature. It does not focus the parallel rays or magnify the object. So, it is just a rectangular slab, isn't it? So, how it works you can see here. So, when light rays from an object enter a negative index material from the free space, they are basically negatively refracted, okay, at the first instance. Okay. So, and then again when they go to the second interface, you have another negative refraction which focus them back. Okay. So, what is happening in this kind of slab? It is forming two images, right. So, here you are getting a real non-inverted images inside the slab, and you can get a second non-inverted image, okay, in the free space after the slab. Okay. So, this is how you are basically getting the negative index material work for you. Now, while doing so, this is basically how the propagating wave is going on. This we have already seen that you can use this material for restoring the evanescent wave. So when the evanescent wave enters this material, it is already in a very weak form, but then because it grows exponentially in this material, it goes up to this level. But then again, when the wave exits and come to free space, it decays. But the good thing is, at this particular point, the level of that, or the strength of that wave is of that mode, evanescent mode, is exactly same as what was there earlier. So you actually have the same whatever information you have here is again you are having here. You are not losing anything, right? So a negative index material lens basically overcomes the diffraction limit by a unique mechanism that could restore the evanescent wave, which is discussed, right? So what is the behavior of the evanescent wave? In free space, evanescent wave basically decays exponentially with distance. So you can express this in this kind of form: exponential minus I omega t plus I kz z. Okay, so their wave vector component is basically kz, which is nothing but I kappa z, and that is coming as I square root of kx square plus ky square minus k naught square, right? So they are basically decaying near fields, okay, and you can see that this particular term is imaginary and positive, so the field is basically decaying, right? Now inside negative index material, this evanescent fields get amplified, and that is happening because in that case the kz, which is nothing but minus I kappa z, will be written as minus I square root of kx square plus ky square minus epsilon mu omega square by c square. So this is negative imaginary, right? So that is coming because you have epsilon and mu both negative in negative index material, so their product will remain positive, okay, and this term you are getting as negative imaginary. So what happens when you get negative imaginary? That means the evanescent wave basically grows exponentially inside your negative index material slab, and you get the function to become exponential kzz. So this growth basically fully compensates for their decay in the free space, and you can restore the evanescent mode at the imaging plane to their original amplitude, okay, which are basically carrying the sub-wavelength information, and you can do the perfect imaging as we discussed, right, and shown in the earlier slides. So for the propagating waves now, which basically carry larger scale information, they also behave differently in a negative index material. Their amplitude basically remains constant, but their phase kz equals minus square root of epsilon mu omega square by c square minus kx square minus ky square basically is getting reversed. So this basically causes their phase to accumulate to 0 from the object to the image plane, okay. So you are getting a perfect image because both your propagating and evanescent waves are fully recovered, and an ideal negative index material lens can produce a resolution which is far below the diffraction limit. But there are some limitations of negative index material lens as well, so we will discuss that. So Penrose's perfect lens is basically a theoretical breakthrough showing that evanescent waves can be amplified for super resolution imaging. Now there are some practical limitations because perfect lens conditions are extremely strict. First of all, they must be lossless, isotropic and impedance matched. Now since realistic metamaterials are all dissipative and they are lossy because of the plasmonic resonances, okay. So despite you have the theoretical possibility of having a perfect lens, making one in reality is extremely difficult, right. So any real world losses or anisotropy or impedance mismatch in negative index materials, which are kind of irresistible in the current designs, okay, they all can eliminate the desired effect. So that means the negative index materials created so far, okay, are all very lossy and highly dissipative. and this is why there has been no far field demonstration of super resolution using planar negative index material slab, except for a few fundamental results which are demonstrated in the microwave range. So, let us look into some near field super lens, which is basically a simpler version of a perfect lens. So, we are talking about near field super lens because they can also achieve subwavelength resolution. So, they are basically a simpler version of perfect lens. So, this design is easier to realize because it does not require negative permeability, that is optical magnetism. So, only it works with negative permittivity. So, how it works? This near field super lens is basically based on quasi-static approximation, which applies when all the system dimensions are basically subwavelength or smaller than the wavelength of the light that is involved. So, under this condition, the requirement for super lensing of p polarized, or you can say TM mode waves, can be simplified to the condition that the lens's permittivity epsilon must be equal to the negative of the host medium's permittivity, that is epsilon h. So, you should have epsilon equals minus epsilon h. Okay. So, in that case no optical magnetism is required. So, you can have a simplified version of the lens compared to a full negative index material. So, here is an image of an optical super lensing that is achieved using silver slab that is operating at ultraviolet wavelength. So, these objects are having very tiny slits which are sub-wavelength, but because of this silver super lens, you can see the evanescent waves get simplified and the information can be captured in the images, right. So, this is the schematic that, or the cartoon that tells how it works, and this is how it was exactly made. Okay, you have PMMA, then silver and some photoresist, then these are like the chromium slits, okay, and on a quartz substrate. That is how it was made. Now, couple of important things to remember here. So, when you are making a near field super lens, first important point will be the choice of the material. Since you are focusing only on negative permittivity in the near field super lens, so it must be made from a material which has got a negative dielectric response such as noble metal, right. So, you can choose silver for this application because it has significantly lower loss in the optical range as compared to other material like gold, copper and all. Now, there is a role of surface plus bond. Okay. So, similar to the perfect lens, here in the near field super lens, the super resolution capability basically relies on the surface plus bond polaritons at the interface between the metal and the host medium. So, here it is silver and air. So, these surface modes are basically excited when the condition for the near field super lensing will be met, that is the permittivity of the silver will be equal to -1, that is negative of the host, here it is air. Okay. So, this specific frequency is often called as the metal's surface plus bond frequency. Now, if you consider silver, this will correspond to a wavelength of 340 nanometer, which is typically in the near UV range, right. Now, what are the application? So, while it is limited only to the near field zone, this near field super lensing has many interesting applications such as biomedical imaging, sub-wavelength lithography and other near field optical devices. Now, if you come back to this particular design what we have seen earlier. So, here what is happening, the main factor that is working is the growth of evanescent waves, and that is giving the super lensing effect because of this silver slab. So, people have done experiment to evidence this super lensing. So, they have done this silver based near field super lensing in the optical or the UV range. So, here you can see that the evanescent waves are basically enhanced by this silver slab, and this enhancement continues until the material loss becomes dominant, right. So, an enhancement factor of over 30 was recorded using an optimized 50 nanometer thick silver film. Okay. So, this was the structure that was used. So, silver slab was having a thickness of say 35 nanometer, which was sandwiched between these photoresist layers, and they use 365 nanometer illumination wavelength, which is in UV. And what was the result? They could capture images of gratings that you can see here with a 60 nanometer half pitch, that is typically lambda naught by 6. Okay, and they can also record 40 nanometer line width, okay, from this structure, that was confirming that they are able to capture the sub-wavelength resolution. Now, people have also seen the growth of evanescent waves and superlensing effect using silicon carbide slabs. So, there also people conducted experiments to see the superlensing. So, this silicon carbide based near field superlensing was seen in mid infrared range. Okay. So, it basically uses surface phonon polaritons instead of plasmons, and this is possible because silicon carbide's phonon resonance property basically gives a negative permittivity. So, again you are using that negative permittivity, but the origin of that effect is not plasmon here, it is basically the phonon resonance. So, this is the experimental setup. As you can see, a 440 nanometer thick planar silicon carbide slab was used as a lens, which is sandwiched between two 220 nanometer thick silicon dioxide films here and here, and then you have this object plane. So, this is the ACM image of the object plane which is being used, and this is the probe. Okay. So, the best superlensing performance was obtained at a wavelength of 10.8 micrometer, where basically you are getting that negative permittivity condition, that is the real part of the permittivity of the silicon carbide was equal to the negative of the real part of the silicon dioxide permittivity. So, what was the result? A resolution of lambda naught by 20 was achieved in this experiment, which was obtained using a near field scanning microscopy that could collect the image transferred through this silicon carbide slab. Okay. So, here is a table that can compare the two near field super lenses. So, one is based on silver, another is based on silicon carbide. So, the mechanism is different. The first one works on surface plasmon polariton, the other one on surface phonon polaritons. Here you can see the wavelength range. This one works for UV 365 nanometer, the other one for mid IR, that is 10.8 micrometer. The lens material, here it is silver slab and here it is silicon carbide slab. The thickness of the lens, here it was 35 to 50 nanometer, whereas here it is 440 nanometer. The supporting layers were photoresist layer, here it is silicon dioxide thin film, each with 220 nanometer thickness. Here the evanescent wave amplification was more than 30, and mainly it was done because of the surface plasmon polariton or surface plasmon resonance. Here it was from phonon resonance, and resolution achieved here was lambda naught by 6, and here you can see you can go up to lambda naught by 20. So, experimental method, here it was used near field optical lithography, and here they used near field scanning microscopy. So, what is the key advantage? So, it basically works in optical regime. So, UV imaging or nanolithography can be the applications, and silicon carbide one works in IR regime. So, you can use it for thermal or bioimaging applications. Right. So, let us discuss what are the limitations of silver near field super lens. You can see that a silver near field super lens basically operates at a single frequency, where the lens condition, that is permittivity of the silver, will be equal to minus the permittivity of the host, that is satisfied. Now, for silver slab in air, the condition was satisfied at 340 nanometer, which is in UV. Now, it is very difficult to extend this wavelength, especially beyond the visible range, due to mismatch with realistic host materials. Now, to satisfy the lens condition in the visible range, the host medium need to have extremely large permittivity, so you require high index dielectric. But in reality this kind of material do not exist which has got very large permittivity, or basically they suffer from very strong absorption. So that is the practical limitation of making this super lens beyond visible range. Okay. Now the solution here comes from instead of using silver you go for metal dielectric composites. Okay. So if you can use metal dielectric composite as a lens material, that offers significant advantage. Okay. So the composite films can have effective permittivity, that is epsilon E, which depends on the permittivities and the filling factors of both metal and dielectric components, right. So this added flexibility, so you can actually change the volume fraction and tune the permittivity, and this flexibility allows you to satisfy this equation, okay, at different wavelengths, and that basically gives you tunable near field super lensing operation across visible and near infrared ranges. So a schematic concept is shown here in this particular figure. So you can see a metal dielectric composite slab basically acts as an alternative to the bulk metal slab. So you can consider the thickness to be D here, and you have host medium D1 and D2 on the two sides. So this provides a practical path to multi wavelength, or you can say tunable super lensing. So the optical properties of this metal dielectric composite can be described using effective medium theory, which you have discussed earlier. So you can basically treat this composite as a homogeneous medium which has got a permittivity epsilon E. Now how you can obtain this permittivity epsilon E, that basically depends on the metal and the dielectric permittivity and also the volume fraction. Okay. So we can see in details that how you get this. So the d-dimensional composite material that comprises of metallic particles which have got permittivity epsilon m and volume fraction is p, and that way you understand that the dielectric component will have permittivity epsilon d and the volume fraction will be 1 minus p. So this formula basically gives you an estimate of the effective permittivity, and that can replace the solid metallic slab. Now the ability to tune a near field super lens imaging super lens depends on this relationship between this epsilon E, the light wavelength lambda, and the metal filling fraction. So you can find your operational wavelength that would be basically satisfying this super lensing condition. That is, you have to find the real part of this effective permittivity for a desired or tunable volume fraction at the desired operational frequency, and that should be equal to the minus of the host permittivity at that operational wavelength. So what you are achieving here is that you can change the metal filling factor and you can change epsilon E, and that will allow you to satisfy this. So you basically get a broad operational wavelength control for near field super lensing application using this method. So this principle is also shown here. Okay. So you can consider a silver silicon dioxide composite film. So you can it's a silver silicon dioxide composite film. So you can describe this using a Drude model, and if you consider the composite film with a metal filling fraction of P equals 0.85, you can compute the effective permittivity, which is basically shown here. Okay. So this tells about the effective permittivity behavior of the composite film. Okay. So for a pure silver slab, you are basically getting this super lensing of condition met at a particular wavelength, but here you can see that all these different points are marked. So A, B and C are basically the permittivity of the host of air, silicon carbide and silicon. Okay. And using a composite film, that basically gives you greater tunability and allows you to avoid the significant losses. So the solid lines here are basically the real part of the permittivities, and the dotted lines basically show you the losses. Okay. So what are the advantages of using semiconductor host here, silicon or silicon carbide? They basically have large permittivity, so they are good for host medium, and when you have large permittivity, that allows you to shift the operational wavelength outside the plasmon absorption band. So you can avoid even large losses that is coming from the large or high imaginary permittivity, and that improves the resolution. So finally you can see that the imaginary part of the permittivity allows you to have minimal additional losses. So these are the other 2 points marked for P equals 0.85. So this is for silicon carbide host, and this is for silicon host. So both you can see they are outside the absorption band, so they basically allow efficient NFSL operation. So here is the conclusion, that by selecting suitable host material and adjusting the metal filling fraction P, you can make a composite metal dielectric near field super lens that can operate at any desired wavelength within the wide visible near infrared range. So with that we conclude here. Thank you for your attention. If you have got any query, please drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.